Hiya! So in this recording we're going to be looking at, or in this video, we're going to be looking at another example of conditional expectation. So we're actually going to look at a previous example and kind of go from there. And so the example we're going to look at is the one where we rolled a six-sided die, looked at the number of divisors, and then rolled until we found one of those divisors. So let's kind of go back and see how the problem was set up, and see how conditional probability kind of fits in here. Or law of total expectation more specifically. So here, remember that we roll a six-sided die, and then I look at the number and write down all of the divisors of that number, right? So remember here we had d of x representing the divisors. And then what we said is, okay, what I'm going to do is I take this number and I'm going to roll my six-sided die repeatedly, until I roll one of the divisors. So what we're going to do is we're going to let x be the number rolled by the die, so that's the first time, right? So this is just a standard, is the discrete uniform distribution. Discrete uniform distribution, right? Here p is equal to 1/6 because each one has 1/6 chance of coming up. And then we're going to let y be the number of rolls needed to get a divisor of x. So since each time we're rolling discretely, right, we're doing one roll at a time, this in itself is a geometric distribution. Metric distribution. And what we saw last time was that this had distribution. What we saw last time is that the probability in this case is dx over 6. So here, dx, remember, is the divisors of the number. And so we're going to ask is, okay, what is the conditional expectation of y given x equals x? So let me highlight that. Conditional expectation of y given x equals x. And so how do we write this? This is just the conditional expectation. So it's y given x equals x. Now what is this? Remember that this is geometric dependent on x, right? Once we have our x, then it's geometric from there. And geometric distribution, we already know what this is. So if this is geometric, remember that in this case, the expected value is just 1 over p. And in our case, for p here, it's just dx over 6. In other words, we get 6 over dx. So nice and easy. It's not too bad. So in this case, it was easy peasy. So how about the expected value of y? This is a little more complicated, but here we're going to remember that y itself is dependent on x, so it might be good to use the law of total expectation, right? So we end up with this. Now here, this part, we already kind of know. This is going to come from here, right? So the idea here is that if e of y given x equals x is equal to 6 over dx, then this function y given x, right, is equal to 6 over dx. In other words, the function here, e of y given x, can be represented as this random variable. So this is just looking at functions. Let's look at functions. And so what we have here is this part in the middle can be rewritten as 6 over dx. In other words, I can pull the 6 out in front. I have 6 times 1 over the expected value of 1 over dx. Now this part we have a calculation for, right? We know how to do this. This is not difficult. This is we know how to do something like this, right? We have a formula. So if we recall the formula here, this is just like if I have e to the x, right, this is just the sum of x, px equals x, right? So we're going to, but here we have a function. So if we have a function, let me show what happens with a function, g of x. Remember that this is just g of x, right? So here our function is 1 over dx. So we have to sum over all the x's. Well, what x's do we have? We have 1, 2, 3, 4, 5, and 6. So we have x is equal to 1 all the way up to 6 of 1 over dx. And then the probability that x is equal to x. Now this part here, this is, remember we have a discrete uniform distribution, right? And the probability is 1/6. So in other words, here I can substitute 1/6 and I can actually pull the 1/6 out, right? So 1 over 6. And then I get 1 over dx. And here we can just plug in our numbers. So we get 1 plus 1/2 plus 1/2 plus 1/3 plus 1/2 plus 1/4, right? So here, if you recall, these are the numbers for our x's. So x equals 1, x equals 2, x equals 3, x equals 4, x equals 5, x equals 6. And if you kind of recall, like for example for 4, 4 has 3 divisors, right? So that's why there's the 3 in the bottom. It's 1, 2, and 4, right? So 3 divisors. So this part here, if we try to solve, we're going to have to do a similar denominator so we can add. And here the same denominator is 12. And we end up getting something like this. Yeah, this is 3. And if we sum all of these together, we get 37 over 12. And I'll leave it like this for now, and we'll see why in a few minutes why I'm leaving it like this. So what we end up having is, so let's go back and solve e of y. E of y is 6 times e of 1 over dx. And 1 over dx, or the expected value here, is this, right? So in here we can plug this in. It's 1/6 times 37 over 12. And now you see why I kind of left the 1/6 there. These 6's cancel. And I'm left with 37 over 12. And 37 over 12 is going to be roughly equal to 3.08333, etc., repeating. So the 333 repeat forever. And that's it. So we expect there to be roughly 3 rolls to get a divisor, which kind of makes sense, right? Because like most of the time, like for 2 of them we have greater than 3 or 4, right? So we're expecting it to push towards the 3 range, which makes complete sense. Okay, and so we'll stop this video here. And in the next video, we'll look at another example of this. So I'll see you in the next video. Bye.